Okay, now that we've collected our data, we're ready to look at what our data shows us. And we're not going to do much math in this chapter, but we want to see a picture of the data. Now, in your textbook, the data set that they use in the textbook, for example, for the example throughout the chapter, has to do with IQ scores, differences between children who lived with high lead levels and low lead levels. I'm going to leave you to read that in your textbook, and I'm going to use a data set that is the pulse rates in beats per minute of females and males, and we're going to look at those, and that's what we're going to look at on the slides. So that way you'll get more than one example of what we're doing in this chapter. So when we look at the data, we want to see them, and we're going to concentrate on shape, center, and spread. And to that, we're going to add change over time. Now, in your textbook, they talk about center, they talk about variation and distribution, and that has to do with the spread is the variation, and the distribution is the shape, as well as outliers add to our shape. And then again, change over time, we may be looking at data over a long period of time, and that can tell us some important things too. But shape, center, spread is a lot easier to remember than the list in your book. So first, let's look at the data, and we're just going to look at these quickly. First of all, we look at the symmetry, and then we look at how many peaks there are. So when we have a symmetric data, it's going to be bell-shaped, and there are other symmetric shapes that we'll talk about. But it means that you could fold it in half, and both the left and right sides would be the same. Then we have some non-symmetrical or asymmetric graphs, and it may be right skewed and it may be left skewed, and we'll talk about the differences between those. And then we have unimodal. Modal is a mode is a data point that occurs the most often. Unimodal means it has one peak, and bimodal means it has two peaks. And we'll look at a data set later in the slides that we can describe as bimodal. First of all, bell-shaped. This is a normal curve. We'll talk about what that means in Chapter 3, but this is the curve of standardized tests, where most people score in the middle. You have a few people who score in the upper regions and a few people who score in the lower regions. But this is a shape that you're going to become very familiar with. Now, mound shape is similar. It's also symmetric, but notice that it keeps its curve direction throughout the whole range of scores. Remember, I'm going to back up here. Maybe I'm going to back up here. Oh, shoot. In the bell-shaped, see how it curves in and then it curves out and then it curves in again. So just notice how the bell shape is different from the mound shaped. And then another symmetric shape is a uniform distribution. And a uniform distribution would be something like, we look at numbers, we have a six-sided die, and we toss the die. If the die is fair, we will get a uniform distribution of the six faces of the die. And then the sketch of the data looks like a rectangle. Now, when we have asymmetric distributions, it's skewed to the left, and you look at where the tail points to. So in this slide, the tail points to the left, so this is a left skewed distribution. Now in this one, the tail points to the right, so this is a right skewed distribution. Now, outliers are things that don't fit with our pattern. Now, they may occur naturally, they may be due to an error in recording, they may occur because we measured incorrectly, or the observational unit may be fundamentally different. So if we go back and you think about the children's story, The Ugly Duckling, there was a swan in the brood of ducklings, and the swan looked different than her duckling brood mates. Well, the swan, the baby swan, would have been, which is a cygnet by the way, so the baby swan would have been fundamentally different than the ducklings, and so that would have been an outlier. We're going to talk about frequency distributions first, and we're going to start with tables, frequency distribution tables. And when we have data sets, we need to organize them, because otherwise they're just a jumble of numbers and it's very easy to get mixed up. And so what we do is, the first thing where we start is, we start with a frequency distribution table, and we do a little groundwork, and it helps us to understand the distribution of the data set, and then we also have a basis for constructing graphs. So here's the data that we're going to use, and so we have the set of females, the set of males, and we're looking at their pulse rates in beats per minute. And what we've done is we have divided the data into classes. So we can see that, I'm going to go back to the data in the previous slide. And so if you look at this, the lowest score was 60. And if we look at it, the highest score looks like it's going to be 124. So what we're doing is we want to divide out our scores from 60 to 124. And what we did was we divided it into classes. And it's very important that in the classes that each individual can only fit into one class. So notice how our pulse rate, and we're only looking at the females for our frequency table here. Our pulse rate goes from 60 to 69, and then it goes from 70 to 79. So it's very clear that if someone has a pulse rate of 69, they'll go into this first group and not into the second. We can't go from 60 to 70, 70 to 80, 80 to 90, because then if someone has a pulse rate of 70, which group do we put them in? So it's very important that they only fit into one group. Now, I will tell you that sometimes we use symbols to help us with this as shortcuts. So we go 60 to less than 70, and we go 70 to less than 80, and 80 to less than 90, and less than 100, and less than 110, and less than 120, and less than 130. And so by using that less than sign, then automatically at the top of the class, if it's 70, it goes into the next class up, etc. Now, The class limits are the smallest numbers that can actually belong to the different classes. So our class limits on this are going to be the 60, 70, 80, 90, 100, 110, 120. And so you can see we have our lower class limits right there. Then our upper class limit is the largest number that can belong to that class. And you can see that those are going to be the upper. I'm going to go back here. Those are going to be the upper numbers on our class description. Now, we have class boundaries, and those take out the gaps. So what happens with the class boundary is it's going to be halfway between the upper class limit of one class and the lower class limit of the next. So let's go back to that. And so you can see that as we go between these two classes, here is our class boundary, halfway in between there. Then we have our class midpoint, and the class midpoint, what we do is we add the lower limit and the upper limit together and divide by 2. So we're going to take 60 plus 69 divided by 2, and when we do that we get 64.5 is our class midpoint. Now, we're not going to do much with class midpoint, but if all we had was this frequency table and we didn't have the data table that was a few slides ago, we could find a really good estimate of the average of the data by taking the frequency times the class midpoint and then adding those numbers up and dividing by the number of individuals in our data set. But we're not going to need to do that very much. Okay, now class width. Class width is from lower class limit to lower class limit. So it's 60 to 70, which is 10. Or it's 69 to 79, which is 10. It is not. It is not. It is not. Oh, darn it. Let's try that again. It is not from the lower class limit to the upper class limit. So it's not 9, it's the 10 that we find either from lower class limit to lower class limit, or the 10 that we find from upper class limit to upper class limit. Now, when we're going to do a frequency distribution, we want to determine the number of classes, and it should be somewhere between 5 and 20. Now, how do we do that? Well, sometimes you just decide, and it makes it important. Is it going to be 10? Is it going to be 20? But I will tell you that another way to look at it is to just look at the number of data points that we have, take the square root of it and round it and make it something that's convenient. So let's look at that, and let's go back to our frequency table, and we have 40 individuals in our data set. Okay, 40, square root of 40 is going to be more than 6. So let's look at 6. And so I'm going to just do that. We had 40 individuals. And we want to look at the square root of that. And it's about 6. It's a little more than 6. and our data went from 60 to 124. So that's going to be 64 is going to be our difference. 64 divided by 6 is going to be about 10. So 10 pounds makes, oh, I'm sorry. So 10 beats is going to be a really good interval for our classes. So let's look at this and let's go on. So we did the minimum value, maximum minus the minimum. We did that over here, divided by the number of classes. Well, here's the number of classes that I had there, and so that's how I got to about 10 as my class width. I'm going to look at the minimum value, and then I'm going to find a convenient value below or above. So if our minimum value was 62, we'd still use 60 because that makes sense when our class width is 10. And then using the first lower class limit and the class width, then we proceed to list all the other lower class limits, and then we find the upper class limits. And then we just simply put a tally mark in the appropriate class. Okay? Now, sometimes we want to do relative frequency rather than the number. And when we do the relative frequency, we simply take the frequency divided by the sum of all frequencies. This is going to be a decimal number. And then a percentage frequency is just a relative frequency times 100. So in other words, we took our decimal times 100 to get a percent. Okay, so again, we came up with our lower class limits, we came with our upper class limits, we looked at our frequency. I'm not sure what happened there. We looked at our frequency and we saw that there was a total. So then what we did to get a relative frequency, and I'm going to say they already changed this to a percent, and so we simply took the 12 divided by 40 times 100 to get that relative frequency on that last slide there. Then there's another thing we can do, and that is the cumulative frequency. And the cumulative frequency just says this is everybody who's less than that. So we have 12 that are less than 70, we have 26 that are less than 80. That's 12 and 14. We have 37 that's less than 90. That's 12 and 14 and 11, and so on and so forth. When you get to that highest class, then you know this is everybody that is in your data set. So again, here are those tables that we just looked at all together side by side, where we have the frequency table, we have the relative frequency, and this is the relative frequency in percent, and then we have the cumulative frequency. Okay, now again, like I told you before, normal distributions are of extreme importance in statistics. They're bell-shaped, they start low. So let's think of our graph here. They start low, the number increases, and then it decreases. And it's symmetrical, and again we have the curve, curves in, curves out, curves in again at the end. There is a special notation, and we use that special notation. An N, capital N, stands for normal distribution, and the first number is the mean, and the second number is the standard deviation. And we'll talk more about these symbols in the next chapter. Gaps in any distribution can give you clues. They may be from two or more different populations. For instance, let's look at this. We looked at a bunch of pennies. So randomly selected pennies. And then we looked at the frequencies of their weights. And we have something very different. Now remember, pennies before 1983 are mostly copper. Pennies after 1983 are mostly zinc because of the high price of copper. But here we go. So let's look at this. So let's look at our frequencies. Oops, I'm sorry. Let's look at our frequencies and notice that we have 37 that are down here in the lower end of the weights. We have 35 that are here in the upper ends of the weights. Well, we don't have anybody in the middle. So this tells us that these are probably the pre-83 pennies, and these are the post-83 pennies. So we have good evidence that these are actually two different populations.